So in the last class, we discussed how increasing the effective stress, increasing the effective confining stress or cell pressure, the stress in the soil, all right? So we saw that with increasing effective stress, the soil underwent consolidation. Of course, we have to allow drainage. If we allow drainage, then only consolidation will occur. So when consolidation occurs, the soil it densifies, all right, it compacts into a denser configuration. So the density of the soil increases. So particle to particle contact increases. The stiffness of the soil increases. Modulus of deformation increases. And ultimately, we can say the shear strength of the soil increases. So we have discussed in detail, we have seen what are the various conditions, undrained and drained conditions, then how we apply the cell pressure at various stages, what happens when we apply the cell pressure in an undrained condition, how the pore pressure develops initially, and when it reaches the effective stress of the state of the soil, the previous effective stress of the stress state of the soil, that is the pre-consolidation pressure. So then what changes in the behavior takes place? All right, what changes in the behavior takes place? All right, so we have assumed the soil to be a spring, and we have correlated the behavior of the soil to the spring, and we have seen when it deviates away from that behavior, right, when it deviates away from that behavior. So we have seen the structure of the soil, how it changes over which changes in the effective stress on in the soil, right? So one thing you kindly note that I have been using the term effective stress, right? So that is the most important part. So all of these plots whichever I have done, so consolidation of the soil takes place only when the effective stress within the soil changes. So kindly keep that in mind, and that will happen only when we allow the drainage from the soil. So the pore volume, it has to reduce. The water from the pore volume has to go out, and the volume of the voids has to reduce, and that only then only there is consolidation in the soil. And we saw what is pre-consolidation pressure and how we can approximate the behavior of the pre-consolidation stage, all right, of that stage of the soil. So we ultimately came up to this slide where we saw that we have the B parameter and we have the A parameter, and the B parameter is mainly the change in pore water pressure, how it defines the change in pore water pressure. We change in the effective in the cell pressure, in the total confining pressure, and we have discussed that A parameter is the parameter which defines the change in the pore water pressure, which change in the deviatory stress, or in the axial sigma 1 stress. All right, so now before going on to the changes, what will happen when we now apply deviatory load? When we apply sigma D, we are now applying sigma C, right? So whatever delta sigma C we are applying actually, or sigma C we are applying, ultimately whatever it is happening is that delta sigma 3 is changing, and delta sigma 1 is also changing at the rate of delta sigma 3. So here also we are applying, so that is delta sigma 1 is basically equal to delta sigma 3 when we are only applying cell pressure. When we apply sigma D, ultimately we have sigma 1 is equal to sigma d plus sigma 3. So when we apply delta sigma 3, so it will be delta sigma 1. So now there will be application of axial stress here in this direction, and the sigma 3 will be in this direction, confining the sample from all sides, right? Confining the samples from all sides, all vertical sides, of course, right? So before going on to the behavior, how the pore pressure will develop, what will be the changes in the pore pressure, all right? If there is drainage is allowed, what will be the drainage, all right? What will be the drainage condition? So before going into that, we have to discuss what is the critical void ratio. So we have in our undergraduate courses, we have known that we generally define soil into two stages. One is the dense sand or over consolidated clay, and one is the loose sand or normally consolidated clay. So basically it is, one is a dense state, a stiff state, and one is a loose state, right, or a soft state. So now when we apply shear stress on this two type of soils, the soil which is in the dense state, what it will happen is that the volume of that soil will tend to increase. The volume of that soil will tend to increase with shearing of the sample. So when we suppose in a direct shear, which we have studied in our undergraduate course, so in a direct shear, if we apply shear onto the sample with, for a normal stress, particular normal stress, we apply the shear force. So what will happen? For a dense soil, the volume of the sample will increase. Right? Volume of the sample will increase. So this is dense sand. And similarly, for loose sand, when we apply shear stress or shear force, the volume of the sample or sand will compress. It will get compressed. So we have the loose sand where there is compression taking place. So with time there is compression taking place, and ultimately there is a strain or stress level when delta V ultimately becomes 0. But delta V becomes 0, right? The volume has already changed whatever it needs to change. So this is the total volume change. So delta V is basically increments, all right? So increments. So here there is no increment at a particular stage. So at that stage, so delta V becomes 0. So the volume that we have at that state, all right, we need to measure, and the volume of voids, basically the volume of voids that we have at that point divided by the volume of solids, we have the void ratio, which is actually the critical void ratio. Similarly, when there is a dense sand and we shear the dense sand, so initially of course there will be some amount of compression, very slight compression. So there will be some elastic or shear deformation within the particles or some rearrangement, all right. And then as soon as it gets sheared, as soon as the particle starts rolling over each other, so we will have an expansion. Then similar to the normally consolidated soil, after a particular expansion in the soil, so this is the total expansion. After a particular expansion of the soil, there will be no volume change in the soil. So the volume change will be 0. Right? So this is the total volume that it has expanded. Alright. So this is the expansion for the dense sand, and this is the compression for the loose sand. Now again here we will have to measure what is the total volume of voids. Alright, by the volume of solids we will get the void ratio, which is the critical void ratio. So this is just an introduction. We will discuss this in detail. So thing is that when we shear a sample, if it is dense, then there will be expansion in the sample, but that expansion will not continue. It will not continue on forever. It will expand to a certain state, and then with continuous shearing, it will shear at a continuous volume. It will go on shearing at a continuous volume. Alright, so there will be no change in the void ratio. The shearing will continue. Alright, so at that particular volume only. And the deviatoric stress which will be required to cause the shearing, that will be constant. Alright, so at that moment del sigma d also will become 0. Alright, and that sigma d which is required to cause the shearing, it will remain constant. Alright, we will see why I am saying this. Alright, and how we apply the load in the triaxial cell, we will see. So the dense sand will the volume of the dense sand will become constant at a particular volume. Similarly, the normally consolidated soil, after compressing up to a particular level, also it will constantly go on shearing at a constant volume. Right? So the void ratio at that point is the critical void ratio. So if we plot it in terms of void ratio, so for the normally consolidated soil, we will start at the higher void ratio. So the volume of voids will be more. Alright, and in this dense state, the volume of voids will be less. Alright, volume of solid will be same in both the case. So this is the volume of voids. So when we will shear the sample for a particular effective confinement, okay, so remember these terms, remember why I'm emphasizing on this. So it is effective confinement, so not total. So it should be effective equal to total minus the pore water pressure. Alright, so you may see that if I take total stress 200 kPa and pore water pressure 100 kPa, we are at the same effective confinement 100 kPa. If I take total stress 400 kPa and pore water pressure 300 kPa, we are at the same effective stress 100 kPa. So both of this soil, for both of this condition of total stress and pore water pressure, the soil has the effective stress of 100 kPa confinement. Alright, so these two soils will behave exactly same. It will behave the similar way. Alright, so I am saying effective confinement. So for the same effective confinement, alright, when we will shear the soil, and if it is the same type of soil, that is, whether it is dense or loose, it is the same type, means same grain size, same specific gravity, same plasticity, alright, index, whatever, means the same type of soil. If we then shear, so the dense state of the soil will increase in volume, so the void ratio will increase. While the loose state of the soil, the void ratio will decrease. And ultimately they will tend to one same void ratio for both the case while the shearing is continuing. Okay, so remember that the shearing has to continue. It is under constant shearing only that we have achieved this. Alright, we will see what are the different void ratios corresponding to different effective confinement, okay, and how we define that. So when we shear the dense soil will expand and it will tend to a constant volume, that is a constant void ratio. And similarly, this loose sand will contract or compress, and it will tend to a constant void ratio, and ultimately both of these void ratio will be similar for a particular confining effective stress or particular effective confinement, as we say, right? So this void ratio is called the critical void ratio. So before going into understanding this, all right, so this is basically the definition of critical void ratio. So we have to understand what is the critical void ratio. So before going into that, so let us just revise and understand what is basically effective confinement, what is basically this total stress, and what is pore water pressure, and delta sigma, delta u, and similarly what is delta sigma dash. All right, so if you remember, we had one sample. So we had one sample inside a soil at a particular depth of z. We had a pore water pressure of gamma wh, right? So this is the sample. So here this sample had an effective stress state of sigma dash is equal to sigma minus u, where sigma is equal to gamma unit weight of entire whatever is. So this is gamma bulk, this is gamma saturated, if there is anything on top, all right, everything, all right, so that is, we consider it to be gamma z, all right, and we had a pore water pressure which is gamma wh. So gamma z, we say that it is suppose 200 kPa at this state, and the pore water pressure, we say that it is 100 kPa. So effective stress in the soil is equal to 100 kPa at this point. Okay, at this point. Now we took it out, and ultimately the stresses, total stresses on the sample will be 0. There will be some residual pore water pressure, and there will be an effective stress state. Then we apply the cell pressure again. So we put it on the triaxial cell, and we start applying the cell pressure. Now if you remember, the soil at the initial stages, when we will go on incrementing the cell pressure, it will behave as a OC soil, over consolidated soil. So the B will not be equal to 1. It will be basically less than 1. So delta U, all right, delta U means we have a pore water pressure here. So we have a cell pressure sigma C, all right. So sigma C, suppose we have 2 kPa now. Then we increased up to 3 kPa, the sigma C. So delta sigma C at this stage is 1 kPa, that means. So 3 kPa, which is the final sigma C, minus initial one, it is 1 kPa. Similarly, delta U is, so at point of sigma C equal to 2, we had a U, pore water pressure, and at sigma C equal to 3, when we increased it to 3, we have a pore water pressure. So delta U is the difference of these two, U1, U2 minus U1. So we have, suppose we say it is 0.2 kPa. All right, so we applied delta sigma is equal to 1 kPa, and we saw that delta U is 0.2 kPa. So we can say there is an increase in sigma dash as well, all right, because 0.8 kPa is still left unbalanced. So 0.8 kPa increase in effective stress is taking place. So in that way, what will happen is that we start from somewhere, suppose, so this is 100 kPa. So this is the state that we have to reach. All right. So this is the effective confinement of sigma dash is equal to 100 kPa. So we start from somewhere here. All right. So sigma c is equal to 1, 2, 3. Right. And this way we will go on increasing. So as we go on increasing, u will also go on increasing. All right. So u will also go on increasing, but delta sigma u will not be equal to delta sigma will not be equal to delta u. All right. So the increment in the effective increment in the cell pressure will not be equal to the increment in the pore water pressure. The pore water pressure will increase slowly in the initial period. So we can say that there will be a change in the effective stress in the soil. So the effective stresses will change. So ultimately, as we go on increasing sigma c, all right. So we reach 50 kPa, all right, 50 kPa. We reach then 100 kPa. Right. So when we reach 100 kPa, we see that U is equal to suppose 80 kPa. No, it will not be 80 kPa. It will be much lesser. All right. So 20 kPa effective stress cannot be. It has to be 100 kPa. All right. So it will be much less. All right. So around it will be around. Actually, it will be around. It will be around 40 kPa. Okay. So slowly, when we reach sigma c is equal to 200 kPa, we will see that the pore water pressure will reach 100 kPa. So sigma c dash, or the effective confinement in the soil, will now reach the 100 kPa mark, as it was in the in situ condition. So in the initial phase, what will happen is that when we go on sigma c, the effective confinement will also increase in this manner. Why straight? Why horizontal? All right, because it is undrained. So since it is undrained, there cannot be any delta V. Right? There cannot be any volume change. So the volume of the sample, whatever was during the sample, that volume has to be retained. So the void ratio, whatever it was in the initial state, that will have to be conserved. Only thing is that in the initial stages, since the soil has already been consolidated to a particular effective stress state of 100 kPa, all right, so the soil is now stiff, and when it is the effective confinement is less than 100 kPa, until and unless it is 100 kPa, the soil will behave as an over consolidated soil. So delta U will be less than delta sigma. All right. So 100 kPa, it is 40 kPa. Similarly, if we reach suppose 150 kPa, so it will be around 70 kPa. All right, it will be around 70 kPa. If we reach around 180 kPa, it will be around maybe so we can see. You can see. So let us write it here. So at sigma c equal to 50 kPa, the pore water pressure we measured is suppose 20 kPa. So effective stress is 30 kPa. So it is here 30 kPa. Then at 100 kPa, when sigma c was 100 kPa, so we have delta sigma c is equal to 50 minus 100, we have 50. All right, and we had 40. So we have 40, 100 minus 40, we have 60 kPa. Alright, so we have 60 kPa. Alright, and what about the delta U? So delta U is equal to 20, 40 minus 20, we have 20. So the B is equal to 20 by 50, it is less than 1. Alright, so similarly at 150 we had 70 pore pressure, and ultimately when we reach sigma C is equal to 200 kPa. Now we reach 200 kPa sigma C. That is the total cell pressure of 200 kPa we have reached, and we see that pore water pressure reading is now showing 100 kPa. So the effective stress in the soil is now 100 kPa. So we have reached this condition here. All right. Now this is for isotropic consolidation. Okay, consolidation which occurs in triaxial cell. So we say that isotropic consolidation. Now we will consider the two cases. One is undrained and one is drained. And we will see why in undrained we assume the sample to be unconsolidated. And in drained case, we consider it to be consolidated. Right? Now suppose, now we have reached this state. Now we increase the cell pressure to 250. Sigma C is equal to 250. Now what will happen to U? So we will observe U now is equal to 150 if it is undrained. If it is undrained. So you can see what is sigma dash effective stress in the soil. 250 minus 150 we have equal to 100 kPa. So basically it is remaining at the same point. It will remain at the same point. It will not move. So that is why in undrained case we are considering the soil to be unconsolidated. Okay. Now if it is drained, all right. So let us consider the case here. So we have increased up to 250 and the pore water pressure is 150. So effective stress is 100 kPa. So it is still here. So we can now do two things. We can keep the pore water pressure constant, and we can go on increasing the cell pressure. So if I go on increasing the cell pressure, if I suppose increase the cell pressure from 250 to 300, all right, while keeping the pore pressure same, so at 150, so that means what happens? The effective stress in the soil is now changed to 150. All right, so we have allowed drainage while keeping the hydrostatic pore water pressure to be at 150. In fact, we can do that. All right, in the triaxial test, we can do that. We can control the hydrostatic pore water pressure. We will see that is called the back pressure. That is called the back pressure. So nowadays we can control the pore water pressure, hydrostatic pore water pressure of the sample. So we can do that. So we see that the effective stress in the soil has increased from 100 to 150. So what will happen? There will be consolidation in the soil. So the soil will now move to, this is 200, so 150 will be somewhere here. So the soil will move to this point here. So there will be volume change. So the void ratio will change. void ratio will change. So that means the soil is consolidated. We can achieve the same amount of consolidation by lowering the pore water pressure as well. Alright, if we keep the sigma C constant at 250, alright, and we lower the pore water pressure from 150 to 100, if we lower the cell pressure from 150 to 100, then also the effective stress will be 150, right? And same amount of consolidation in the soil sample will take place. All right, so this is basically addition of surcharge. So this condition is addition of surcharge in the soil sample, and this condition is lowering of the water table in the in situ condition. So both of the cases are possible. All right, so if we allow drainage in the sample, the void ratio in the sample will reduce, the volume of the sample will reduce, and there will be consolidation. But as long as we do not allow any drainage from the sample, we go on keeping increasing. Suppose from 250 we increase up to 300 without allowing any drainage in the sample, we will see that the pore water pressure also increases to 200. So ultimately the effective stress in the sample will remain at 100 kPa. So it will remain here itself. It will not move from here. So that is what is the undrained case. Alright, and if there is drainage, so there will be consolidation. So that is the drainage. Alright, and there will be reduction in the pore water pressure. So now before going into further analysis, so here we have used the term P dash. Alright, so P dash. So I would like to first define what is P dash. Alright, and why exactly we use the P dash, alright, instead of sigma C or sigma 3. Alright, of course why we will come to it later when we will study the stress path. So for now let us define what is P dash. Right, so first of all we have studied what are the stress invariants in stress strain chapter. Alright, so I, J. Alright, we are not going into details of that. So P is basically the mean stress. Alright, so the basic advantage of this is that it is a stress invariant. Alright, so it is independent of axis. It is independent of axis, of the axis system mostly. Alright, and P is defined for three-dimensional case. For three-dimensional case, P is defined as sigma 1 plus sigma 2 plus sigma 3 divided by 3, and it is also called the mean. That is why it is called the mean stress. All right, and this is actually a volumetric stress. All right, volumetric stress. So delta P or increase in P, delta P is increase in P means, all right, or change in P, will only result in increase or decrease in volumetric strain, all right, or volumetric strain. All right, so there will be no shearing in the sample. And if you see, it is basically these 2 point joining. All right, if this is sigma 2, all right, if this length represents sigma 2, all right, if this length represents sigma 1, all right, and if this length represents sigma 3, then this is the p coordinate. All right, so it is basically the I mean uh, the direction which is taking into consideration all of the three total principal stresses. All right, so this is p. Now p dash, if you remember, if we have pore water pressure does not have it is not direction dependent, it is same in all direction, so we have u. All right, so if we put here minus u minus u minus u, ultimately it will result in sigma dash 1 dash plus sigma 2 dash plus sigma 3 dash by 3. All right, the u will cancel each other out. All right, so ultimately cancel each other out means it will be taken out, that is thrice u by 3 and ultimately minus u, so we can write that p dash, all right, is equal to p minus u. It is equal to sigma 1 dash plus sigma 2 dash plus sigma 3 dash by 3. All right, this is of course for 3D case. This is of course for 3D case. In case of triaxial test, all right, we have the axisymmetric condition. Therefore, P we define it as sigma 1 plus twice of sigma 3 divided by 3. All right, so that is P, and P dash is equal to P minus U. All right, so this is the effective confinement which we say. So this is called this term is called effective mean stress. All right, effective mean stress, or we can also say effective confinement in terms of triaxial test. So this is of the mean stress. Now what about the deviatoric stress? All right, so in a triaxial test we not only apply sigma c, we also apply sigma d. All right, so we define the deviatoric or distortional, we define the deviatoric or distortional or in general terms shear stress, right? So in three-dimensional case, so we define it as q. All right, we define it as q. So q is given as 1 by root 2 root over sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. All right, so that is the three-dimensional case, and this distortional or deviatoric stress, it is always perpendicular to the principal this confining stress. So q is always perpendicular. It may be in this direction, it may be in this direction, whatever direction it may be, but it is perpendicular to that direction of p. All right, it is always perpendicular. So that is what causes the shear failure of the soil. Shear failure of the soil. Now So this causes distortion or shearing of soil mass. So this is what causes the shearing of soil mass. Now this is of course three-dimensional case. In case of two-dimensional case, not two-dimensional case, in case of axisymmetric case, that is the triaxial case. In case of the triaxial test, so we have the axisymmetric condition. So sigma 2 is equal to sigma 3. Alright. So what we have here, we can put sigma 2 is equal to sigma 3. Alright. Therefore, sigma 2 minus sigma 3 is 0. This cancels out. Alright. And here we can put sigma 2 in 3 in place of 2. So sigma 1 minus sigma 3 and sigma 3 minus sigma 1 whole square is the same thing. Alright. So we have root 2. So if we put it out, so 1 by root 2. Alright. So we have square root of twice of sigma 1 minus sigma 3 whole square. Alright. So root 2 gets cancelled. Root 2 gets cancelled. Right. Root cancel, and then this is equal to q is equal to, ultimately we have q is equal to, we have sigma 1 minus sigma 3. Now here you see, if it is undrained condition, change in delta P will result in delta U. Alright. So basically P dash will remain constant, or delta P will be equal to 0. Only in case of drained condition, will there be consolidation. Alright, and that means P dash will increase. So in that case, delta P will be equal to delta P dash. Alright, so delta P dash equal to 0. But we will now see that deviatoric stress is independent of pore water pressure. So this is sigma 1 minus sigma 3. So now what I write in terms of, if I write it in terms of effective stress, so suppose I want to write in a q dash, right? So ultimately we have sigma 1, so sigma 1 dash minus sigma 3 dash, right? So is equal to sigma 1 minus u minus sigma 3 minus u. So ultimately this, if I break it out, so this becomes plus and this becomes minus. So ultimately we have sigma 1 minus sigma 3, which is equal to q. So deviatoric stress is independent of increase or decrease of pore water. So delta U has no effect on deviatoric stress. So this is a very important consideration, because when we load a particular element, when we load a particular soil, if that load causes increase in pore water pressure, then the effective confinements are, the values of effective confinement reduces, all right, or the effective confinement reduces, but increase in that deviatoric load ultimately causes increase in the deviatoric stress, all right. So there is no change, or there is actually increase in the deviatoric stress, and there is decrease in the effective stress. So this is a very dangerous conditions. So if this condition prevails, at a lower load only the soil will start to fail. All right. So in during liquefaction, what happens? Delta U becomes such that we have sigma dash is equal to 0, or actually P dash is equal to 0, but Q will remain there. Q will remain there because sigma 1 is there. All right. So sigma 1 in that case will be equal to sigma D, whatever load we are applying. All right. So in that case, that soil will undergo shear failure. All right. And it will deform. It will shear off. if that shearing or divisory stress is consistently being applied there. So that is a very important case. So we need to be able to identify when there will be pore pressure changes, and will it lead to changes, how much will it lead to the changes in the effective stress. So we have understood what is the changes in undrained and drained condition, and when the soil is remaining unconsolidated and when it is consolidated, right? So just for further, there is another. So this is basically this whatever we have studied here. So this is basically called the Cambridge notation. All right. So this is called the Cambridge notation. All right. So this is called the Cambridge notation, and it is the latest. Whatever it was developed to, I mean, explain the stress development in the soil sample, and it was very efficient. It was observed that this system is very efficient, and therefore it is mostly followed nowadays. All right, it is mostly followed nowadays. So this is the Cambridge notation, and before this notation was developed, before this PQ, we call it PQ. All right, so P is confinement, Q is divisory load. All right, so before that was the Cambridge notation was developed. So we had another notation, we call it the MIT notation, all right, or of defining average and shear stresses. So here what we define is that we define it in terms of the center and the radius of the mode circle. All right, so basically the average stress, average confining stress, all right, average confining stress and maximum shear stress, maximum shear stress. All right, so if we consider a plane where there is a maximum shear stress, so that shear stress is given by, so here actually this is T, all right, this is T and this is S, right? So ST notation, so ST notation, right? So S is equal to sigma 1 plus sigma 3 by 2, so average. So this center of the mode circle. All right, so that is 1, and then T is defined as T is equal to sigma 1 minus sigma 3 by 2, which is the radius of the mode circle, and this is the plane with the maximum shear stress. All right, so this is actually the maximum shear stress. All right, so if we move on to another plane, we can see that the shear stress will reduce. So this is the maximum value of the shear stress, right, tau max. It is very easy to see from here. So if if we rotate the plane, all right, so the shear stress will reduce. It will not go beyond this for this particular stress configuration, of course. All right, this particular stress configuration. If we have a lower stress configuration, so here we have this maximum stress here at this point, and we have this average confining stress. So this is the ST notation, right? So here also, if we see, so ultimately equal S dash, that effective average confining is equal to S minus U. All right, and this is ultimately independent of pore water pressure. So T is equal to total stress, shear stress is equal to total effective shear stress as well. So that is actually the case why we need to know what is the pore pressure development. Okay, and how we correlate that to the angle of internal friction and the cohesion, we will see it in the later slides, right? So just a definition so that you may understand when we see the plot what is P and what is Q and how we do the this analysis, right? Okay, so now moving on. So now moving on to what is critical void ratio. So to understand that critical void ratio, so before understanding that, we have to understand the change in void ratio during consolidation. Right, so you know that in consolidation we have the sample, and it is fitted inside a cylindrical this box, we can say, all right, can say, and we go on increasing the load, all right. So here it is basically K naught consolidation. So during the oidometer or consolidation test that we do, all right, in the oidometer when we do the consolidation, the consolidation that occurs is basically K naught consolidation. So K naught means active pressure, all right. So active, not active, sorry, what it was, earth pressure at rest condition, all right. So K naught we can define it as in terms of Poisson's ratio mu by 1 minus mu, all right. And the K naught value is mostly, it is in the range of if we consider sand, then if we consider dense sand, all right, and loose sand, then K naught will range from 0.4 to 0.5. Again, for normally consolidated clay, all right, it is mostly in the range of 0.5, all right. It may go a little bit this side, mostly this side around 0.6, but it is mostly around this. So here sigma v, if you say this is sigma v, all right, and if we consider sigma h here, all right, so sigma h is basically half of sigma p, all right. So we can say that there is some amount of shearing in the sample, all right. So we have seen that Q is equal to sigma 1 minus sigma 3, all right, or T is equal to sigma 1 minus sigma 3 by 2. So in this consolidation, so there is some amount of shearing, all right. While if we go for consolidation in the triaxial test, so here whatever stresses we are applying, all right, sigma c, we are causing increase in sigma c, right. So same amount is increase in all direction, all right, all direction. So here sigma v is equal to sigma h, all right. So this condition is called the isometric consolidation. All right. So now when we apply sigma v in the consolidation test, sigma v, obviously sigma h will also increase, and ultimately p dash is equal to sigma v plus twice of sigma h by 3 will also increase. So when we do the test, we observe, what we do is we generally measure the volume, volume of voids. Ultimately we plot it in volume of the void ratio with the effective stress. All right, so in consolidation test, since the drainage is allowed, so it is ultimately whatever load we are applying, ultimately it is getting converted to effective stress. So sigma v total whatever we are applying is sigma v dash, and sigma h whatever we are applying is equal to sigma h dash. So we can directly plot the this result. So here we see that for this particular confining stress we have this void ratio. Then if we increase the confining stress, that means we increase sigma v dash, so sigma h dash will also increase, so p dash will also increase. So we increase the confining stress, and ultimately the soil will consolidate, all right, because the drainage is allowed. So this is the new void ratio now. So the void ratio will keep on decreasing. So the void ratio will keep on decreasing as we are going on increasing the confining stress or the effective stress as we are going on increasing. So this is K naught consolidation in the oidometer. So what I want you to know, understand is that for a particular effective confinement in the K naught consolidation stage, there is a particular void ratio. So if we go on increasing the confining stress, the void ratio will go on decreasing. That means drainage is occurring, all right. If we do not allow the drainage, ultimately pore water pressure will develop. The confining stress will remain at the same point, and therefore effective confinement will remain at the same point, and therefore the void ratio will remain at the same point as well. So only when we allow the drainage is there a change in the void ratio. That means there is consolidation in the soil and there is increase in the effective stresses. So this is K naught consolidation in oidometer. So you know that when we load the sample, so we have a curve like this, all right. So we take this E naught, all right. So this is one load. Then again we load it. Again there is a curve like this. So this is the E1. All right, so this is the load. All right, so for the consolidation test, then we calculate the CC and the CV parameter, all right, from the curve. So that is, of course, in the other chapter. We are not going to discuss that in detail here. Now in the triaxial cell, when we are going to apply sigma C, it is in all around increment, all right. So what happens is that we are doing isometric consolidation. All right, or we can also say isotopic consolidation. All right. So here again, when we allow the drainage to occur, if we allow drainage, there will be consolidation. All right, there will be consolidation with increase in the effective confinement. So void ratio is getting decreased. If we do not allow drainage, obviously there will be only increase in the pore water pressure and the point will remain exactly at the same. So there will be no change in the effective stress. Alright, delta sigma dash or delta p dash will be equal to 0, or delta sigma dash will be equal to 0. Right? Sigma and u may go on increasing. So the point will remain there itself. So no change in volume, no change in effective stress as well. Undrained condition. In drained condition, application of load results in change in volume, no change in pore water pressure, and therefore there is consolidation. All right. So this is what the consolidation, how the consolidation happens. So we have to have the drainage. All right. So this is the consolidation for the clay. Same thing. All right. If we have the release of load, we have a recompression curve. All right. But the consolidation state is preserved in the soil. So again it will trace back this. Again we have the pre-consolidation pressure here, again normal consolidation here, release of load. Again we will come back here. So this is the pre-consolidation. From here onwards, so this will behave as a over consolidated soil, this particular phase. From here on, again this in this phase it will behave as normally consolidated soil. At this phase, this is the pre-consolidation pressure. All right, in this part it will behave as over consolidated soil. From this phase onwards, again normally consolidated in this range. All right, so in this all of this analysis, one thing you remember is that we are allowing drainage to occur from the sample. Right now, all right, so we have the K naught consolidation and we have the isotropic consolidation. All right, so in the triaxial test and in the oedometer. Now what will happen when we shear the sample? We will see it in the next class. Okay, so next class we will see.